quiz is going to happen.
I should have written it down right when I thought about it. Let me think. Decided it's going to be, next Thursday. There should be plenty of time. So we're going to have a quiz. 3-1 and 3-2. You're out of the rotation, poor little dude. 3-1, 3-2 next Thursday. That's October 5th. That's a good writing day for you, Jeff. Oh boy. Thursday. Okay. I try to do at least 2 quizzes before every test, just because those are good little gauge points. Don't forget the homework's not due the day of the quiz. You have until the day of the test. Okay. So I think last time I stopped when we finished multiplication. We haven't started talking about division yet. And I want to ask you a couple of different scenarios to get us into division. So here's one scenario. If I have a box of 30, where's your good one, Jeff? Box of 30 erasers. And I want to divide them into 6 bags. How many would end up in each bag, right? Evenly. How many will end up in each bag? And then the second kind of situation would be, I have a box of 30 erasers, and I want to divide them into bags of 6 erasers each. How many bags do I end up with? So there was something that came up last time we were together, and I said there's so many different problems that would end up being a multiplication problem, but the problems are so disparate in concept, right? Or like an addition subtraction problem. You guys kind of with me? So for example, I have 7 toy airplanes, and Billy has 12 toy airplanes. How many more does he have? That's 12 minus 7. I have 12 toy airplanes, but Billy stole 7 of mine. So it's the same math problem, but a very different concept to start with, right? And like I said, they're not going to understand that they all have the same kind of math approach to answering them. I see this all the time at higher levels. Students that aren't able to do math as well are the students who don't see how this problem is exactly the same as that problem, just different numbers, right? So some students treat every problem as an entirely different universe, and I'm like, no wonder you got to see the thread that underlies all of them, which is not the most immediately easy thing to do. Of course, what's the answer for both? 5, but it references different things, correct? 5 what's in problem number 1? 5 erasers end up in each bag. In this one, you need 5 bags, right? So the math doesn't care about the physical interpretation of the numbers. It says 30 divided by 6 is 5. Leave me alone. But these are completely different physical realities, correct? You guys with me? Okay, I like it. I like it. So, exactly like we saw with addition, subtraction, we're going to have kind of multiple ways to approach a problem. Does it make sense that this first one, we would call this a sharing division problem? So it would be more obvious that it's sharing if I said I have 30 erasers and there's 6 people. If I want to divide them evenly, how much does each get? So here I'm talking about bags, but I'm still sharing the erasers with each bag, correct? So that's the sharing approach. This one, unfortunately, this is what I kind of prepped you for. The second one is called a measuring division problem. And of course, we already have a measurement model. But, so this one is called a measuring division. Okay. I'm not hyper concerned about the words, although I will probably use them on like a quiz or a test. So you do have to be familiar with them. But I'm not going to ask you like a definition question, right? Okay. So can you imagine how you would have a very young person try to do these problems? I mean, let me see. How would you set up a physical situation? What would you do?
Blocks.
You can use blocks, sure. So for the very first problem, what else so you'd have 30 blocks, and then you'd have.
You have like 6 bowls or 6
Sure,
bags.
sure. Right, is that cool? So you could have 30 blocks, and then you let the kids kind of figure it out. All right, and of course, I got some videos I'm going to show you. They're going to be basically doing exactly that. You could also just have 30 erasers and 6 bags, and just have them sit down and parse it out. So a lot of the time, what you're going to be doing, you're going to be starting with physical things they can hold and do things with, and let them have fun and let them do that. And then you want to connect that with the math behind what they're doing. But they have to first intuit what physically to do with it, because almost every mathematical thing we do has a physical interpretation, believe it or not. A lot of it does. What about this other one? What would be different about this one? You still want like 30 blocks. But now what do you think a kid's going to do to start to work this problem out? If you give them 30 blocks, what do you think a child would do? If you said, I want you to put 6 blocks into each group, what's he going to start doing? Or she? I'm thinking he, because I think it's a boy in the video.
Making groups of 6.
Yeah, it's going to take 6 and put it over there, and 6 and put it over there. What is that? Do you remember what multiplication was fundamentally? Repeated addition. So division is repeated subtraction. Does that make sense? So watch this. This is kind of cool. Coming off of this, what you just said about he's going to take 6 and kind of keep going. So if I start with 30, subtract 6, I end up with 24. That's crazy. I keep coming back to you. I got to put you away. I can't quit you. Okay. Subtract 6. Subtract 6. This is the most exciting thing we've ever done. Okay. How does that illustrate that the answer is 5? Yeah, you subtracted 5 times, right? So, believe it or not, we're not going to do this right now, but this is the first step in getting to this algorithm. Right? That's our standard long division algorithm. That had to be kind of thought up. That there has to be steps that you take a student through before you thrust that on them, right? And again, that's related to a lot of the concern you see about people with Common Core and all kinds of stuff. They're like, wow, they just show them long division. You gotta get them there. You gotta get them to why that even works. Okay. Is that cool? Yeah, okay. So you got 2 kind of major categories for types of problems that end up with division. And conceptually, they are very different. But they both end up with the same problem, same math problem. So who remembers some of the subtraction approaches? So for example, the most obvious one is takeaway, right? Who remembers the next one? Missing addend. And that's where you go, well, 9 minus 6 means 6 plus what is 9? So you're missing something. So the equivalent would be a comparison. I've got 6, he's got 9. How many more do I need to have the same amount? That kind of thing, right? So with division, we have something very similar. It's called the missing, really, John? The missing factor. So you can start a student, right after you teach them the multiplication table, you can say, okay, look at your multiplication table and tell me 6 times what is 18, right? Now we all know that that would lead to division, because you just do 18 divided by 6. But at first they could just find that 6 times 3 is 18. They can see it. So they can actually see what's going on, and they can kind of think, and again, this is a place I wish we would start doing a little bit of algebra, for example, right? Instead of a blank space, why not put a little variable there? Right? Okay, so you got the missing factor approach, very similar to the missing add-end approach. So a kind of a strict definition given A and B whole numbers, A divided by B equals C, and also a couple other things. B not equal to 0. A divided by B equals C. C is a whole number. Means A equals B times C. And you can see how that idea is where the missing factor approach comes in. You can rewrite a division problem as a missing factor multiplication problem. This is groundbreaking, I know. I think last time I had already talked about, did I already talk about division by 0? Did I get a little overzealous, or have I talked about division by 0 yet? What happens when you try to divide by 0? Do you know why it's called that? Okay, does anyone know why it's called undefined? All right, let me let you know. I'm gonna let you know. Remind me, why is, so go with me, this is gonna seem silly. Why is 6 divided by 2 equal to 3, using what we just talked about here? Why is 6 divided by 2 equal to 3? 3 times 2 is 6, it's crazy, right? The number 3 is defined in such a way that when you multiply by 2, you get 6. Is everybody cool with that weird-ass way I just said it? Okay, I agree, it's a very weird-ass way, but you'll see why I did it that way. So what would 6 divided by 0 have to be? It would have to be the number defined in such a way that when you multiply it by 0, you get 6. Is there any number defined to do that? Any number I multiply by 0, I get 0. So we don't have a number defined so that when I multiply by 0, I get 6, so we freaking call it undefined. Is that all right? Okay. Undefined. So that's a really cool example of something that somebody might have told you that at some point, and you just forgot it. But more than likely, I don't think people really go that extra step and explain that to you, right? Everything we do, there's got to be a reason for it. So one big thing I want my students always to do is, if I'm ever doing something like you have no idea why the hell I'm doing it, just ask me. Or generally, like, why the hell is this? If I'm not able to tell you, then that means I shouldn't have the job I do, right? That's my job, is to explain why the things work. Right? Okay. Anybody else besides undefined? Anybody ever had a teacher tell you this was something different, a different word? Somebody do me a favor. Anybody have a calculator real handy, or a phone with a calculator? This first problem you don't have to do. What's 6 divided by 1?
6.
Holy shit. What's 6 divided by 0.1? Some of you guys might know. 60. What's 6 divided by 0.01? 600. Does that work? Okay, cool. I like it. Because I keep dividing by 1/10, which means multiply by 10, right? So what's happening, 6 divided by 1 over 1,000 would be 6,000. So 6 divided by 0.001 is 6,000. As I keep dividing by smaller, the answer keeps getting bigger. So just imagine I keep getting smaller and smaller and get really close to zero. The answer is just going to keep growing without bound. So another thing you could call that is infinite. Everybody with me? I wouldn't call it that for little tiny ones, right? Not necessarily. I don't know when infinity comes in, to be honest. Anyway. So that's kind of cool. So sometimes you'll see somebody call it infinite. And real quick, just to really push, maybe bring bad memories for, I don't know. Slope, do you guys remember slope? What was slope again in words? Rise or run, or change in y over change in x. So rise rhymes with y's, which is cool. So the y's are on top. Rise over run. You guys all with me? Remember that? So 6 over 2 would be you rise 6 and you run 2, right? Rise or run. 6 over 0 means you rise 6 and you run none, and then you rise 6 and you run none. So doesn't that just go straight up? That would be infinite slope. Just instantly you're there. You guys kind of with me. So normally you're like, if we move over a little bit, now we're here. We move over a little bit. If you have infinite slope, you're here, and then you're there. You're way there, right? Another reason why it's called infinite is because you can relate it to slope, any ratio. You can relate it to slope. Okay. Enough about that. So let me give you a couple of definitions. So we've got the missing factor approach. This guy. What's the official name for division? Somebody knows. So you got sum for addition, difference for subtraction, product for multiplication, quotient, right? That's the least used ones. That's the one everybody kind of forgets. Poor little quotient. So I would say C is the quotient, right? Or you can even say A over B is a quotient. What are the parts called? All right, I got you. So it sounds a little bit like business. Dividend, divisor, which kind of makes sense. That's the thing you're dividing by. So what's his job? He's the divisor. I like it. And again, I am not overly concerned about the words, right? I really doubt the curriculum for like a first, second, third grader would be too concerned about those words either, but you should always know a lot more than what you're going to explain. Okay. Oh, do you guys remember the 4 fact families from before? In fact, in the homework you had to do some for like base 5 and base 6, I can't remember. Right, so some of the homework you had to do that same thing. So you get something very similar here. So like, for example, 4 fact family, 6 times 3 is 18, remarkably enough. So then 3 times 6 is also 18 because multiplication has the commutative property. What are the other 2 elements? Let's see if you guys remember. Yes?
I like 6 divided by 3, or 18 divided by 3 is 6.
Good. 18 divided by one chunk is the other chunk. So then you can do 18 divided by the other chunk is the first chunk. I like it. So these 2 combine to be this. Therefore, this divided by one of them is the other one. Just kind of like breaking them up. Okay. And so that leads to a little side note. If I had to solve this equation, for example, the funny thing is, something you want to learn from algebra is you could just switch. You could just do this. And that's part of the 4 fact family. If 7 divided by x is 21, isn't 7 divided by 21 equal to x? This is the part of the 4 fact family. Or you could do times x divided by 21, or just switch the damn things, right? Because of course that has to be true. And then you reduce that and you're done. Yay. You guys all like it? Okay, I like it. So that's funny. 4 fact family seems really weird. I don't know what it looks like to you guys. Maybe on one level it's like, well, yeah. But it actually has direct practical application. Okay. Oh, so now we get some cool stuff. So let me ask you guys about remainders. So can you guys do this for me? Use repeated subtraction to figure out this here. Use repeated subtraction to do that division problem. What I always say is if you're not sure what to do, draw a little duck or something. So to me it looks like you're doing, or try it, honestly try it, that's probably a better thing. Try that, make mistakes now, if you're gonna make any. I'll start to catch up to you guys. Oops. So 54 minus 17. 37, is that cool? And then subtract 17 again. So far I got 1 to go in. Here's another one. 20. Here's another one. Subtract 17. 3. So there's another one. Oops. Not another one there. So 17 goes into 54 how many times? 3 times with 3 left over. So of course, you can write it like that. That's what you start off with when you first learn long division. You write the big ass R, right? Later we learn to do it with fractions, but of course normally we learn this before we learn fractions. Okay, or at least how to operate with fractions, right? We don't look at 54. In fact, it wouldn't even be given like this. It would of course be given like this. So it's an operation instead of a different kind of number, right? Okay, nothing too amazing there. What does that mean, though? What does that really mean, that the remainder is 3? What does that really mean? Does anyone know? True. 17 would have gone in evenly into what? So don't think of it as 3 left over. Think of it as there were 3 too much to begin with. That's why there's 3 left over. If only it would have been 51, it would have went in evenly, right? So that's really what the remainder is all about. So how can I write 54 then? Based on what we just did. How can I kind of break it up a bit? Okay, now go further, because didn't we just figure out it goes in 3 times? 17 goes in 3 times, right? So what's 54 then, isn't it? 17 times 3 plus 3. I like it. So if it would have been 51, 17 would have gone in 3 times even. I like it. It's a real easy little thing to not realize about remainder is it gives me information about, man, if only it would have been 3 less, it would have went in nice, right? I don't know if any of you guys, I'm not going to do this. Oh no. Why am I even going to write this down? Because I'm a weird math teacher. Do you guys, I don't know if anybody remembers doing stuff like that. Now, let me ask you a question. Did you ever long divide this? Okay. That's a whole other thing. Anyway, that's all I'll say. Okay. But the remainder there would tell me the exact same thing, that if only the top would have been that much less, it would have went in evenly, meaning I could have factored it. But, okay, that's a little too much. Okay. So repeated subtraction is a definition for division. But then we have the problem of sometimes it won't go in evenly, so we pick up these remainders. So when I have, let me use the same notation they do. Where did I put it? Oh, I didn't write it down. It's too bad for me. Oh, here it is. Okay, good. So here's the kind of the formal idea. When I have A divided by B, if it equals something remainder something, that means that A equals B times, normally they have a Q plus R. I can't remember what notation they use in the problem. So just like here, 54 equaled B, which was 17, times Q, which is 3, plus the remainder of 3. Okay. Just to make it all formal. Now, every part of this is going to be a whole number for us right now, because we're still not considering negative numbers yet. Okay. All right, so we talked about the missing factor approach. Then we talked about kind of the basic definition of division is repeated subtraction, just like repeated addition for multiplication. Now let's talk about a different kind of approach to how to show a division problem. What about if I try to use the measurement model? Let's start with one that has no remainder. So let's say I want to do the measurement model to look at 12 divided by 4. What's the measurement model lead to? Yes?
Is it similar to the multiplication that we did?
Sure, but so there was the set model, and then there was the measurement model. Set model was you could draw out this with like little blocks in it or something, right? And you could do stuff. Measurement model implied what for the most part? Number line, kick ass. How would you do 12 divided by 4 in a number line? Yeah, so you got 12. And then the idea is to try to break it. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Holy shit. Okay, that's awesome. Sorry. So you want to break this up into 4 equal groups. This is much more difficult, of course, for a student to work with it at the beginning, because it's not physical stuff, but then you can see visually 1, 2, 3, 4 groups of 3. So I got 3, 3, 3, 3. So that's why the answer is 3. 4 groups of 3. And of course, that's similar. The set model would have, oh shit, 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to make the letter D, because apparently that's what I'm doing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We got 12 of these little melting cubes. So like somebody said earlier, I would just kind of like, I could take a ruler and just start to just break them up into groups of 4, so then you can see 12 divided by 4, so this would be 1, 2, 3 groups of 4. So that, of course, is what you do physically. That's the first thing you would do with a student. Play with these blocks. Break them up into groups of 4, and how many groups do you end up with? How would you do, so that would be, which thing? Would that be measurement, or would that be sharing? So here's the thing. Sharing, you're always going to know exactly how many groups you want to end up with, because you got to start with, I've got $20 and I got 5 people. How many does each person get? So I know exactly how many like groups. In that case, I'm calling a person a group, right? You guys with me? I can also think of it as just hands to throw things into. That's not what we're doing with this, are we? I didn't know ahead of time how many groups. I found out. So this would be the measurement model of division. Is that all right? So measurement model is how when you start with a bunch and then you figure out how many groups you could get into. So you know how much you want to go into each group. Sharing model is when you have a total and you know how many groups you've already got. And you're just trying to figure out how much does each group get. So if I wanted to do, so this is the measurement model. If I wanted to do a set with sharing, I'd start with, oh God, 12. And then what would I do? What do you think a kid would do? And I think I asked this one earlier, but if I wanted to use the sharing model. So like you said, you could have, so this would be 12 divided by 4. So how many groups do I have set up already? I got 4 groups, right? And the question is, how much does each group end up with? So if you totally don't know numbers, and you're really new to all this shit, what do you think you would do to get this going?
Count them individually into the values.
Yeah, you could actually start thinking, put one in each, and then put another one in each, right? You can just slowly build them up. It's sort of like playing cards. That's exactly what we do when we're playing cards. So you put one in each, and you put another one in each, and eventually you get to the point where if they each end up with 3, you have none left. Can't like it. And of course, then you can start to bring in the idea of remainder physically, by putting an extra one in there and say, do the same thing again, and they're like, there's one left. And I'm like, okay, that's the remainder. Okay, cool. I like it. And again, on the video, we're going to see some of this stuff happen. Oh, one more thing about repeated subtraction, and then we'll watch the videos. What if you had to do this with repeated subtraction? Would you look forward to that? Like if I ask you to do repeated subtraction of 26 divided by 19, you're like, I'm down because I only have to do one subtraction. I'm done with that shit, right? The problem here is, so can we improve? This is me doing something a little bit ahead of time, but I just want to see if anybody was already thinking about this. Can I improve the repeated subtraction in some way? So for example, instead of subtracting 1/13, couldn't I subtract 10 13ths? I just have to keep track. So instead of doing minus 13, minus 13, minus 13, minus 13, so then I'm counting, I'm like, okay, now I got 10, and I've still got a lot of, oh shit. You could just subtract 130 and put a 10 next to it, right? So then you end up with 330. And let's do it again, right? Okay. So that's kind of like the second step of the evolution of the algorithm to go towards what we consider long division, what we use. And just to remind you guys, I'm going to have to look this up. Same way I looked up how they say Roman numerals, and then I felt silly because, of course, they had names for the freaking numbers. I need to look up how division is taught in, for example, Russia. That's the first one that comes to mind because I think I had a Russian student a few semesters, a different Russian student, and they showed me because they did division a different way. So when I was teaching algebra and we did x squared plus 6 is divided by, and I did the long division, she came up to me after class and said, I don't know what the hell you're doing. The first time that happened, I was like, oh no, you don't know long division, no? But then she showed me, no, in our country we did this, and I'm like, oh, that's so cool. So I got to look that up so I can show you guys. So it didn't have to be the way that we do it. Okay, so you can see how that could eventually get somewhere too, right? Okay, so let me show you some videos. Then I want to talk a little bit more about section 3.3, and then we'll call it a day. Things from section 3.3, and then we'll call it a day. Let's see. So we've already got sort of a way, we'd already talked earlier about a way to tell if one number is bigger than another. So there's a couple ways to tell. Do you guys remember? So one of the most basic ways that a child can keep the numbers in order is the chant. 1, 2, 3, 4, 5, 6. And we talk about the fact that when they first learn that chant, they don't connect that necessarily with a number of things. They don't look at it in all the different ways a number can be looked at. So why would you know that 3 is smaller than 5? If you're only talking about the chant, because 5 shows up later in the chant. I love it. And then that kind of naturally goes to a number line approach, right? Why would 5 be bigger than 3? Why? Yeah, it's further to the right. I love it. Now, let me ask you this. I've had students in the past that would say something like 3 is smaller than 5 because it's closer to 0. Now, if I allow us to consider negatives for a minute, why is that the incorrect explanation? If so, they got the right answer. 3 is smaller than 5. Fantastic. Their explanation can't be true. Do you guys see why? Which one's smaller, -4 or -3? -4. But which one's closer to 0? -3. So that's a really interesting mistake that's made, that they ended up with the right answer, but their logic can lead to trouble. So as a teacher, this is one big reason why I'm not a believer in scantrons, especially for math teachers. So I don't know, has anybody ever had a math teacher that actually used scantrons? Okay. What I very often will say is, if a math teacher wants you to get a scantron, they're not a math teacher. I don't know what they are, because what's the most important thing? The work, right? But this is the kind of, if you get the right answer, but you're applying logic that won't work later, that's where frustration comes in. Because the student will think, I got it right using that logic before, now he's saying I'm wrong. Screw all this. And that's where students start to think, all this is made up, this is why it's not consistent, and there's no way a teacher could ever find out that that was a problem in the beginning. Do you see what I'm saying? If I can't see the work or the thought, I can't correct it. Okay. So, this, of course, now we want to be a little more formal with how we designate less and greater. So, of course, now we're going to talk about some inequality stuff. So for example, 3 is less than 5, and we've already discussed a few reasons why. We got the chant, we got the number line thing, but there's something more mathematical we could do than those. More computational we could do. Can somebody come up with a different reason using, let me just kind of give the game away a little bit, using addition as to why this is true? Yeah.
You could add stuff to 3 to make it 5.
Say again?
You could add something to 3 to make it 5.
Be more specific.
You could add 2 to 3 to make
Good.
it 5.
3 is less than 5 because 3 plus 2 is 5. Okay, so, right? Is that cool? That kind of makes sense. If I have to add something to what I've got to become something else, then I must have less than that thing to begin with, right? So if it costs $5 in the club and I got $3 in my pocket, I'm gonna need somebody to slip me $2. Don't use that example on the little player. Yeah. Okay. Now let's get, you know what we gotta do. We gotta get more formal. If I'm given whole numbers, A and B, and also, let's see, they use a different notation here, that's right. No, okay. I can't remember because I did it differently later. Then A is less than B if and only if A plus N equals B, where N not equal to 0. And N is a whole number. So just basically N greater than 0. It's basically what we just said over here, just more generally, right? Real quick, what the shit is that, Jeff? Okay. This is a shorthand for if and only if. Jeff, really? Sorry. There's a lot of little symbols in mathematics. For example, just to show you a couple real quick. this means for all, like for all n, blah, blah, blah. This means there exists. Doesn't it look like a backwards element of? Anyway, you don't have to know all this, I'm sorry. This is a little shorthand that we use. So one little thing we do is if and only if. So what all that means is it goes both ways. If this is true, then this is true. If this is true, then this is true. So if and only if just means it goes both ways. If then only goes one way for sure, right? If it's gonna rain, then I'm gonna bring my umbrella. But if I bring my umbrella, does that mean it's gonna rain? No. Okay. If I don't bring my umbrella, then it's probably gonna rain. Now, we can use this to kind of investigate stuff like if A is less than B, then A plus C is how related to B plus C? So if I'm given that A is less than B, if I add C to both of those, of course, all of you guys should know, what should I put here? If I add the same thing to both sides, so 3 is less than 5, correct? If I add 4 to both 3 and 5, now I get 7 and 12. It's still less than, correct? So if I add the same amount to both sides, it should still be less than. But how can I actually kind of investigate this? Well, if A is less than B, what does that mean? There is an N where A plus N equals B. Is that cool? I can immediately write that down. If I know that A is less than B, then there must exist some N where A plus N equals B. Is everybody cool with that? Okay, I like it. So how can I rewrite this then? Let's see, we still have this blank. What did we just say B is? What did we just say A plus N? So I see A plus C, and then there's an extra plus N, correct? So then it's more obvious that that's less than again. This is A plus C. How does that relate to A plus C plus N? Well, it's less than because that other guy's got N more stuff. Okay. Like it. So if you ever wondered how I can make something like 3 less than 5 more complicated, that's how I can do it right there. There was one last thing, and then we'll head out. There's a property called the transitive property. And I'll sometimes call it the duh property. So if I'm older than you, and you're older than somebody, then how do I relate to that third person? I must still be older, correct? I mean, that's kind of like why I call it the duh theorem sometimes. So if A is less than B and B is less than C, then A is less than C. Okay. So again, a lot of the stuff we talk about here is kind of obvious if you think about it for a minute, but if it's brand new to somebody, this ain't obvious. This is all new shit. Can anybody see how I can use this idea again? I have to use it twice. I want you guys to get to the point. If I say A is less than B, what can you immediately write down? B must equal. If A is less than B, who do I have to add something to make it the other one? A. So B is equal to A plus N. Now be really careful. What can you write here for this guy? B is less than C. C equals, do it again, sir?
Anything plus B.
Yeah, just not N necessarily, right? We already said, so we'll just do M. C is equal to B plus M. Is that cool? Doesn't have to be the same number, correct? Okay. So then what does, so watch this. B is A plus N, correct? Oh, this is where you guys really love it when I do this kind of shit. B is A plus N, so can I write this as C equals A plus N plus M? So therefore, A is definitely less than A plus N plus M. That's A plus a lot of stuff, correct? You guys all with me? So then it's really obvious that's true. Now, I agree. From the beginning it was obvious, right? But this is just kind of feeling it out. Okay. That's, I think, is plenty. So, don't forget quiz. Let me get that on the camera for the people at home. Quiz next Thursday.